All right, so now I'm going to talk about the current voltage or IV relationship for a capacitor. You can see it up here in the top right corner. Basically, capacitors have a derivative in their IV relationship, similarly to inductors. Inductors also have an integral in their IV relationship, which obviously brings calculus into our analysis of circuits now. We won't really get into that much in this class, maybe a little bit later. But what I really want you to just notice about this equation is that the current, basically what this tells me is if I have a capacitor, I have some current IC, and then I have some voltage across the capacitor. I'll actually draw that in blue, VC. It's telling me that the rate of change with respect to time of the voltage is directly proportional to the current, okay? So if my voltage is changing, then I have some current flowing. If my voltage is not changing, that would mean that the derivative of the voltage with respect to time would be zero, right? If I'm plotting, actually let me go to black. If I'm plotting something with respect to time that's flat, it's just a flat line, and that's what DC is. There's no change in the voltage with respect to time. It's the same voltage. So if I have a voltage source in my circuit with a capacitor like I drew earlier, this is the exact same circuit that I drew. Let's say that I have a 5-volt source and I ground this. I have my capacitor sitting here. Well, my capacitor current is IC. It's determined by the rate of change of the voltage and also by the capacitance of the capacitor, but the capacitance is a constant. My rate of change of the voltage in DC is zero, right? This is a zero slope line. And so this entire term goes to zero for DC, which is why the current here would be zero, okay? And so that's very important to recognize. Let me write that again, that capacitors are open for DC, which basically means I is equal to zero. Okay, so maybe I shouldn't slam that in there, but I definitely want to write that in here again and just really harp on that fact because it's going to be important. It's very important to recognize. Okay, and so the other thing to recognize here is that, let me go ahead and grab my highlighter, the voltage across a capacitor cannot change instantaneously. Okay, for a resistor it can, but for a capacitor it cannot change instantaneously. The reason being that the current in the circuit is dependent upon the rate of change of the voltage. And so let me go ahead and erase some of this stuff up here. If I were to say that the voltage across the capacitor could change instantaneously, that would mean that I would change this voltage with respect to time, and this dt would be zero. Okay, so if that dt goes to zero, then that means that my voltage changes instantly and my current would be infinite. Okay, and so practically that cannot happen, which is why I say that the voltage across the capacitor cannot change instantaneously. Okay, it's important to keep in mind. I'll bring it up over and over again, so don't worry too much about it right now, but definitely important to mention because it's directly related to this equation. The reason why the voltage cannot change instantaneously is because that would result in dt being zero, in which case IC would be infinite, and that practically cannot happen. Okay, so that's the capacitor IV relationship. That is why capacitors are open for DC, and that is why voltage across the capacitor cannot change instantaneously. Okay, in the next video, I will talk about charge storage in a capacitor, and then we'll get into some charge sharing, which is a very important application of capacitors, and we'll talk about that in the next couple of videos.